So the next question here is, why does the asymptotic analysis matter in the real world? Right? So as of now, we have learned multiple notations like big O, big theta, big omega, right? Small O and small omega, right? Why are these are very important? And more fundamentally, I would say, why is the asymptotic analysis is one of the most important concept when designing an algorithm, right? Now let me explain through an example. Imagine we are trying to solve some problem. So that problem could be either researching or sorting or whatever the problem may be. As we progress through the course, you will see many such problems. Now suppose the number of inputs to that problem. So if you look at this particular column, I'm representing the input here, right? So suppose the number of inputs to that problem is 10 power 3 or 10 power 6 or 10 power 9 data points. So that means 10 power 3, which is 1000 data points, or 10 power 6, let's say, which is 1 million elements in an array. Let's say if you're taking the array as an input, right? So 10 power 9, which is 1 billion elements. So these numbers are not crazy numbers, right? 1000 is very common, right? Even the million is unusual, is not unusual, right? For internet companies like Google or Facebook, Amazon, right? Or Instagram or Netflix, YouTube, million is actually, it's a very small number for them. So these companies handle a million, even billions of queries and interactions regularly. And even the billion is not unrealistic number. For example, so if you take the countries like India and China, right? So if you take the example of India and China, right? And countries like India and China have the populations over the billion of people. And even if you take that example of United States has hundreds of millions of citizens. So governments, internet companies, and the large data sets often deal with an input sizes in millions or billions. So these are very common numbers at an internet scale. So here I'm not talking about unimaginably large number. So these numbers are everyday realities for the large systems, right? Now imagine the problem we are solving is, let's say, sorting. So the problem we are trying to solve is sorting. And I'm not saying any particular sorting algorithm has this complexity. So just imagine, for sake of understanding, that the problem could be anything, or it could be a sorting or searching, or maybe finding the shortest path between the two locations, or maybe other algorithmic problem, right? Assume that we have the 5 different algorithm for the given problem. So the 5 different algorithm, let's say this is my algorithm 1, and this is algorithm 2, and algorithm 3, algorithm 4, and algorithm 5. So algorithm 1 has the time complexity of order of log n, and the algorithm 2 has the time complexity of order of n, and algorithm 3 has the time complexity of n log n, algorithm 4 has n square, algorithm 5 has 2 power n. So to really understand what this means, we need to translate these mathematical expressions into time, right? So I'm converting each of them into time, something we need to understand in the real life, right? That is the reason I'm converting them into time. So we understand what is 1 second, what is 1 hour, 1 day, 1 week, 1 month, right? 1 day, 1 week, 1 month, 1 year, right? You know about all of these things. Let us connect these complexities to actual time. Suppose we take the input size is 10 power 3. Let's say my value of n is equal to 10 power 3. For an algorithm A1, which runs the time of order of log n. So how many operations are required to compute this, to perform this task? So it will take roughly around 9.96, right? So how did we got this number? You can go and Google search it. So you just need to type log base 2 with the 10 power 3. You will get the value as 9.96 operations. Similarly, if my value of n is equal to 10 power 6, so it will require 19.93 operations. So roughly around 20 operations. When my value of n is equal to 10 power 9, and if I'm taking the algorithm A1, which runs the time complexity of order of log n, it required around 30 operations. So you can compute these numbers easily by search engine like a Google by just typing log n base 2. So asymptotically speaking, for the value of n is equal to 10 power 3, we roughly performing 10 operations here. For n is equal to 10 power 6, we are roughly performing 20 operations. For the value of n is equal to 10 power 9, we are roughly performing 30 operations, right? So we are roughly performing 30 operations. Now consider the algorithm A2, right, which runs the time complexity of order of n, right? So in this case, right, if my value of n is equal to 10 power 3, if my value of n is equal to 10 power 3, it performs or it requires how many such operation? 10 power 3 operations. That is 1000 operations are required. If my value of n is equal to 10 power 6, it requires 10 power 6 operations. And if my value of n is equal to 10 power 9, we require 10 power 9 operations. For an algorithm A3, which takes the time of order of n log n, when my value of n is equal to 10 power 3, so how many such operations required? We required of 9965 operations. Similarly, for n is equal to 10 power 6, so we may need of 1.99 into 10 power 7 operation. And when my value of n is equal to 10 power 9, we may require of 2.99 into 10 power 10 operation. Now imagine each operation takes 1 nanoseconds. Imagine each operation takes 1 nanoseconds. So what is nanosecond? Nanosecond is nothing but 10 power minus 9 seconds. We know about this, right? Or I would say 1 billionth of a second. So there are 1 billion nanoseconds per 1 second. So why do we need to assume each operation takes 1 nanoseconds? Because modern processors can often execute the simple operations like comparisons or additions. Roughly, it will take around 1 nanoseconds, sometimes even less than that as well. So this is the reasonably rough approximation to help us to understand the scale. So using this assumption, that means each operation takes 1 nanosecond, right? Now think about for 1000 operations, how many nanoseconds are required? We may require of 1000 nanoseconds. So here we may require of using this assumption, for 1000 operation we may require of 1000 nanoseconds. I'm talking about A2 here, and that is nothing but 1 microsecond. For 10 power 6 value, we may require of 1 millisecond. For 10 power 9, we may require of 1 second. Now think about what happens as my input size increases from 1000 to a million or billion, right? Now think about this. What does 1 hour mean in nanoseconds? First, let's understand this. Then we'll compare. So what does 1 hour mean in nanosecond? 1 hour approximately takes 3.6 into 10 power 12 nanoseconds. Now imagine I have an algorithm A4. So I'm taking an algorithm A4 whose time complexity is order of n square. Suppose I give it to 1 billionth data points as an input. So that means my value of n is equal to 10 power 9. Then n square is nothing but 10 power 9 power 2, which is equal to 10 power 18 operations are required, right? So this means this algorithm performs 10 power 18 operations. So each operation takes 1 nanosecond, then the total time required is 10 power 18 nanoseconds, right? Now, what is 1 year in nanosecond? 1 year is 3.15 into 10 power 16 nanoseconds. Now, I'm going to compare this value with my 10 power 18 nanoseconds. 1 year is approximately equal to 3 into 10 power 16 nanoseconds, right? Now, I'm comparing this number versus 10 power 18. Now, if you divide 10 power 18 by 3 into 10 power 16, you get roughly around 33 years. So, it would take approximately 30 to 33 years to complete this task. Think about that, right? If you have 1 billion inputs and use an algorithm which is order of n square, it would take around 30 to 33 3 years to finish the task. This is the massive amount of time it will take to complete the task, right? Now imagine I have another algorithm with the time complexity of order of 2 power n, right? For my value of, even for the value of n is equal to my input n is equal to 10 power 3, which require how many such operations? So 2 power 10 power 3, which is approximately equal to 10 power 301, right? Which is approximately equal to 10 power 301 operation. Since the Big Bang, the universe has exist, right, for roughly around 4.3 into 10 power 26 nanosecond. Compare these with an exponents, right? So 301 versus 26, that is astronomically larger number, right? Even if you waited for the entire lifetime of the universe, the algorithm would not finish. So again, we are making an assumption, right? What is the assumption we are making? That each operation takes 1 nanoseconds. But this is not unreasonable. Many simple operation takes around nanosecond or even less than that. So the key point is the exponent we are comparing. The exponent value is 301 versus 26. This makes an unimaginable difference. So when we are solving the real world problems, as the complexity increases, the feasibility changes drastically, right? If I have to choose an algorithm, I would obviously pick an algorithm even here with the time complexity of log n here compared to remaining all other algorithms what I have, right? For the input size of 1 billion, my order of log n algorithm takes around 30 nanoseconds. So, right? So, if you look at 30 operations are required to perform this task. Each operation takes 1 nanosecond. That means it will require of 30 nanoseconds. For order of n log n algorithm, we may require of 3 into 10 power 10 nanoseconds, which is approximately equal to 30 seconds, right? Right? That means it will require 30 seconds to compute this task. So let me write it down here. The order of log n takes 30 nanoseconds. So the order of log n roughly takes 30 nanoseconds to compute it, and order of n log n algorithm takes 30 seconds to compute the task. So imagine this is my search query on the Google. Imagine, right? Would you wait for 30 seconds for the search result? Of course not, right? So users expects results within milliseconds or certainly under a 1 second. If search engine took 30 seconds to respond, nobody would use it, right? And billion size data sets are very common today in the internet companies and the large countries, right? And even you can consider the identity verification in countries like India or China. So if you take that example of India, let's say I need to check the Aadhaar identity verification, right? Where the population is exceeded 1 billion people are there, right? Suppose a government system verifies these identity numbers. If the verification algorithm runs with the time complexity of order of log n, it may take around 30 nanoseconds, right? And if it runs on order of n log n, it may require of 30 seconds per each person. So 30 second versus 30 nanosecond, that is the huge difference, right? If a government officer had to wait for 30 seconds to verify each identity, that would be extremely slow, right? Each 1 second feel long in many modern applications. So today people expect the responses within few milliseconds, less than second, right? So that is why asymptotic analysis is so important. So it helps us to estimate how algorithms scale, right? It allows us to predict whether the solution will take nanoseconds or seconds or years or longer than the age of the universe. So the right algorithm for the right problem you have to choose by just knowing its complexity, right? So it will allows us to make a rough estimate of how much time it will take using the simple assumption like the ones we discussed right now. And we always want the fastest algorithm provided it meets all other requirements, let's say memory constraint or the correctness of an algorithm based on the business need, right? So we will decide which algorithm is best, right? So how do we choose the fastest algorithm? We pick the one with the lowest asymptotic order here. So suppose I have the multiple algorithms like A1, A2, A3, A4, A5, and all of them satisfy the functional and the business requirement. In that case, I would choose the algorithm with the time complexity which is equal to log n, because it will solve the problem much faster compared to order of n, order of n log n, order of n square, order of 2 power n, right? And even an exponential algorithm takes order of 2 power n is extremely dangerous. Even the small increase of input size, right, it will make it completely impractical. As the value of n grows slightly, the running time explodes. And later in algorithm, we will study why exponential complexity is so problematic, especially in the topics such as NP hard or NP complete problems. We'll understand these topics little later at the end of this algorithms module. But the key takeaway is this: asymptotic analysis is not just a theoretical mathematics, directly impacts the real world system design. When designing the systems for, let's say, identity verification or sorting the large data set or finding the shortest path between the two locations, right, or searching a people in the database, or let's say search engines like Google, social platforms like Facebook, all of these dependent on choosing that algorithm with the right asymptotic order. So if we ignore the asymptotic complexity, our systems may become unstable at a scale. So if you understand it properly, we can design a solution that scale to millions or billions of users. So that is why asymptotic analysis is one of the most important concept in algorithm design. So that's the reason we should learn the topic of an asymptotic analysis in the real world. That would be a real matter.